Moving away from DSP for a moment, in this video, we'll be talking about how we actually use sensors in the field to get that data that we can apply DSP to later. And so we want to think about how we actually power those sensors, but also how we store the data from those particular sensors. But first off, let's think about the lab, because the lab's a different environment to the real world. Using sensors in the lab is, well, easier. We've got ideal conditions, essentially, that we can control lots and lots of things about them. We can plug the sensors into a computer via USB, and that can give us a connection that we can send the data over straight away. It can also supply power to us. USB typically will give us 5 volts or 500 milliamps for USB type A. So we've got high-speed communications. We've got data that's with very, very little delay. And we've got power associated with it as well. But we can't do that in the field. Not many of us want to leave our laptop by the side of the road or under a bridge for maybe months on end. It'll get stolen or ruined when the rain hits it. It will run out of batteries eventually. And we need to think about, firstly, how we actually power our sensors, because most of these sensors that we're talking about are electrically based. And also, how do we actually get the data off those sensors and use that data somehow? So let's talk about powering sensors first. Different sensors need different amounts of power. Some sensors are fairly power hungry, and some sensors use very little power at all. So those low power sensors, for starters, they might be suitable to use batteries on. And what we might do is we might have a particular sensor that uses a couple of milliamps each time it does a sense. What we might do is, depending on the sensor sampling frequency, we might turn the sensor on, take that sample, store that sample, turn the sensor off, and make it go to sleep for minutes, hours, however long it needs to be. Then we'll turn the sensor on, take another periodic measurement, turn it off. And so using that sort of battery save technology where the sensors and the sensing system is essentially asleep most of the time, we might be able to have something that works off batteries for a year or 2 years or 10 years, something like that. Having said that, there's lots of applications where either we want to do sensing a lot more regularly or our sensors use a lot more power. And so we might put a little solar panel up there. You might, as you walk around, you might see little solar panels around for powering particular sensors and have some batteries there so the sensor can work at nighttime, for example. Or we might use, if we're dealing with water or something like that, have a little impeller system here where we can actually use the water flow to generate electricity with a little dynamo turning around, and that will generate enough power to charge up a battery and allow us to do some sensing there as well. I thought it might be useful to show you a brief case study of some sensing work that I've done recently that shows how this low power operation can work in practice. I developed something called Rat Spy, and the idea is we attach it or put it onto a rodent bait station. Inside there's a little camera, a lighting system, and Wi-Fi. And basically what it does is periodically takes a picture inside the bait station and allows us to upload that data to the web. And on the web, we actually do some image processing to try and work out how many pixels or how much bait there is remaining within that system. That way we can send someone to go and fill up the bait station when it's empty or starting to get empty. We've also got a sensor on there, a passive infrared sensor, to detect where there's movement inside the bait station. When there's movement inside the bait station, we can take a picture and see what's actually eating this bait. We've seen all sorts of things from spiders to rats, mice, through to even a blue-tongued lizard coming into one of these bait stations. But the way we've done it is it's all off batteries. And we've done it so that most of the time, the vast majority of the time, the system is switched effectively off. It's in a deep sleep. And in that deep sleep mode, it draws 200 nanoamps. That's a tiny, tiny amount. And that's probably there for 99.99% of the time. But when something wanders in and wants its picture taken, it'll turn on, it'll come out of sleep mode. It'll take that picture, quickly send that picture off to the web. And now sending that picture via Wi-Fi takes a fair bit of current. So for almost half an amp for about 3 seconds. But then it goes back to sleep again. Besides that, periodically, once a day, it will turn itself on, take a picture and go back to sleep. And it will upload that data to the web so that we have a record of what the bait station looks like over time so we can know whether it's starting to get empty or not. So essentially we're using, maybe it'll be on and using stuff for about 3 seconds, maybe 5 seconds per day, very small amount of time. One thing to keep in mind is, just like the TV commercial ages and ages ago of oils ain't oils, well, batteries ain't batteries. There's lots of different types of batteries, from rechargeable batteries to non-rechargeable batteries, and lots of different types in each of those. Some of these batteries have terrible temperature problems with them that as it gets cold, the performance of the battery will degrade much worse than other batteries. Some of them have much higher energy densities than other batteries as well. So depending on the application where it's being used, will start deciding for us what sort of battery chemistry we want to use with these systems too. I mentioned previously about using solar, for example. You could potentially use wind, you can use water flow. The thing to think about with these is they're intermittent power sources. We've used solar in the field. Here's a picture of one of the things we've used it for, where we're using sensing for little animals using microchips or in the animals, in this case, little mice and rodents and donuts. And one of the things we found with solar is if we put the solar panel in the wrong spot, for example, if it was under the shade of a tree for quite a good portion of the day, well, our batteries might run out. If we have a few days where we're getting not much solar power because it's not much sun, well, our batteries might run out. So there's important considerations to think about there when we're looking at alternative energy sources. Well, let's go to logging data now and actually getting that data from the sensors and from our measurement system. Well, one of the common ways this is done is these little flash memory devices. These have gotten much smaller, much more dense in terms of the amount of storage they can store, and much more cost effective as well. Little 128 gigabyte memory sticks or flash memory devices like this are tens of dollars these days. Whereas 5 or 10 years ago, these would have been hundreds or thousands of dollars. One thing that we can do is use a real-time clock. A real-time clock is essentially a small digital device that gives us the time and date. And it uses very little power. It can operate off a coin cell battery for up to a decade. And once we've programmed it, will tell us, okay, this is the current time, this is the current time. And that can be helpful when we're storing our data onto maybe a little flash memory device. So we can store not just our sensor data, but when that measurement was actually performed, because that can be really helpful. Now, commonly, we might store our data in maybe a CSV format or something like that. A CSV format stands for comma separated variable. And here's an example of one. This is the sort of string that we get out of our GPS receiver. This one here, the GPS RMC string, shows us various data fields like what the time is, what the latitude is, what the longitude is, what the date is, and a whole lot of other variables as well. And these ones also have a checksum at the end, so we can verify whether that data has been corrupted, or we can say, yes, we verify the integrity of that data. So each line in our CSV file will contain a separate number of these strings, but we can apply a similar sort of thing to whatever data we're storing. For example, data from a rangefinder, data from a force sensor like a strain gauge, data from a load cell, data from GPS like what we've got here, data from a flow sensor. If we package it up in here and specify, okay, when was this data collected, maybe using a real-time clock or something like that, and our actual data, well, that allows us to store that in a file and review it later on. What about transmitting that data? There's multiple different ways we can transmit data to somewhere else so that we don't have to go out and physically get this little flash memory device and copy it onto our computer. The main two ways or classifications of transmitting this data would be thinking through physical wired connections and then wireless connections. And for both of these, we've got a number of different options. For wired connections, we've got things like using a serial connection, a UART or an RS-232 or 485 there. USB, which is what we commonly use for lots of different applications. I2C, Ethernet, that's our standard network connection, or CAN buses. CAN buses are commonly used in automotive applications. All the sensors within our car will generally connect to each other and interface using a CAN bus. Now, each of these different sensor systems will have different limitations regarding bandwidth, so how much data they can transmit, regarding range, what sort of distance they can operate over, and the sort of applications they operate in. Likewise, we've got wireless sensors as well. This I extracted from a paper I wrote recently doing a survey of different wireless sensor systems. Once again, we've got sensors that are a cellular type of sensors, like using 4G or NB-IoT, where it uses your mobile phone connections. They tend to be more expensive, but it'll also allow us to work in very long distance applications. We've got shorter distance ones like Wi-Fi that we use all the time. Now, this chip on the side here, on the far left, is an ESP32, and this has inbuilt Wi-Fi and inbuilt Bluetooth in it. So it allows us to stream data using Wi-Fi and Bluetooth. The one right next to me here uses NB-IoT, and because it's NB-IoT, it's a cellular connection, you need to put a SIM card in there so it can connect to the mobile phone network. So these have different costs associated with them, different ranges associated with them, different data bandwidths associated with them, which make them more or less applicable for different applications.